Okay, this is lecture 11, and in the last class you were discussing charge pump based PLL. Do you have any questions? Anything? Did you look through the analysis, or that seems fine, right? Okay, so we will go a little bit more into it now. So in the at the very end, we looked the charge pump based PLL as a multiplier based clock multiplier. Okay, and I will draw the small signal diagram of the PLL as a multiplier. ICP by 2 pi. Then I had loop filter of S. One is KVC over S. The clock divider. Okay. So this one is phi out. This one is phi in. And here F in a steady state, F out is equals to F in, or let me start calling as F ref. So F ref is the reference frequency at the input. F ref. F out is the output frequency, and F out is equals to N times F ref. Okay, and we're talking about type 2 PLL order 3. So here I am saying type 2 and order 3 PLL. Okay, so now for this PLL, loop gain is ICP by 2 pi into loop filter of S into KVCO by S and multiplied by 1 over N. Okay, this is the open loop gain of this PLL, and the closed loop gain phi of out by phi in by phi out by phi in is nothing but N times loop gain of S and 1 plus loop gain of S. Means I am using loop gain and loop filter of S, so just be cautious where I use loop filter and loop gain. Okay, so this is the open loop gain and closed loop gain of a clock multiplier, and we have seen how we analyze, how we get all the parameters for the loop filter, where loop filter was, so I will just also write it here, SC2 into S plus 1 by RC1. This is just a recap of what we saw the other day, C1 C2 by C1 plus C2. Okay, and the loop filter was a simple resistor. This was the loop filter we were using the other day. So here I have a error, phi error. This is plus, this is minus. This one is a output of this is a current, which I can call ICP, going into an impedance producing a voltage V control, and the KVCO is radian per volt. It's a frequency 2 pi. Take into account. Okay. So anything, so we know, right, we can find, given the bandwidth and the phase margin of the PLL, we can find all the loop parameters. We have to make a choice for a resistors depending on the noise. And how did we get the bandwidth and phase margin? That is when we do a noise optimization of the PL. Okay. So at the very end, we also saw, means I just told you we will do the analysis in the end, that if I plot phi noise total, let's say, or let me just put the number which you understand better. If I plot jitter, okay, versus the bandwidth, of the PLL, it may have some kind of this characteristic, where you will have an optimum, some optimum point depending on different noise sources. So this is the bandwidth we would like to choose. Okay. So omega bandwidth dash. So we will see how the different noise sources play the role, but how do you get the bandwidth is after doing the noise optimization for a given power. Okay. So other than this, in the basic, let's say charge pump based PLL design at the block level, it is like done here. Now there are other things. Now let's look at what are the, so this is all we have done the linear analysis. Everything is pretty good here, but PLL is a sample system, and when you come from a sample system to continuous time domain model, there will be some changes. We will look those changes later. For now, you can just trust me for the statement that the PLL, this is a rule of thumb, that PLL bandwidth is, I would say PLL bandwidth is not limited, but is mostly less than or equal to fref by 10 for all the above analysis we are doing. We can choose lesser, lower than the fref, but lower than fref by 10, but fref by 10 is the uppermost limit. We will see this thing in detail when we do a digital PLL analysis. Okay. So now let's look at the, because we have done all the linear analysis, let's look at some of the sources of nonlinearity. In charge pump based PL. Oh, this applies for both your divider n equals to 1 or anything greater than 1. Okay. So what do you think is the first source of nonlinearity which comes to your mind? Pardon? VCO, PFD and other blocks. So let's start looking at one by one. Okay. So first one, you have seen that the dead zone in PFD, if we do not eliminate, that's a nonlinearity, right? You will just keep dithering around the phase error locking point phase error, input phase error equal to 0. But this can be eliminated easily. Okay. Now, other than that, there is actually another nonlinearity in PFD, which is intrinsic, means which is intrinsic to the design of the PFD. So let me just or inherent to the PFD design, inherent to PFD design. Okay, so let me say what this nonlinearity is and how it comes. Okay, so in the 3-state PFD which we have seen, so let me just mark here, this is R signal and then this is V signal. Okay, so I'm considering two cases where this error is TE, and in the other case I just exchange R and V signals, and here R is a reference and V is the VCO output. So now this is V and this is R. It is having the same T error. Okay. So in this case, you see, mean when we plotted the output, we plotted that up signal is like this. We are not considering here till now any reset thing. Okay. And down is like this. Okay. In the other case, you have up signal as only this one and down signal is this. Okay. Both should be TE. This is the characteristic which we plotted for a PFD when we use a PFD in an open loop system. Very clear. This is for the case when PFD is used in open loop system. Here, R is your reference and let me just write it. Your R is reference signal and V is PLL output. Okay, it can be, it's a divided, but V is a PLL output. So if I give you this as a on the, let me just mark here that this on a time scale T, both, and I put this in a closed loop system, what can you expect the up signal in the first case be? Will the up signal change or up signal will remain the same? And in case of, in the second case where your V is leading R, whether your down signal will change or remain the same. So at a given instant, the time error is the same for both the cases. One is positive, other is negative, right? If the system would have been linear, then you would have the same positive or the negative output of the PFD correcting the VCO. So what do you think? Okay, so let me go one by one. In the first case where R signal is leading V signal, whatever phase error up is going high, okay, and up is changing your, means up is getting filtered and changing your control voltage, right? Now as the up changes the control voltage and the oscillator frequency and phase both changes, what will happen to the V signal? So V signal, in place of coming here, what I'm showing you right now, you can be somewhere here. Again, depends on the speed of the feedback, V can be changing, right? Whereas in the other case, you are not changing the reference signal, you are changing the V signal, right? So what will change in the other case will be this, the next reference edge, okay? Whereas in the first case, whatever the phase error means, in the second case, if T is the phase error, you are applying the proportional control, right? In the first case, because of the closed loop system, you are changing the V itself. You get that thing. For a positive input phase error at a given sampling point, this because this is a sample system. For a positive phase error, you are actually changing the feedback signal, so you are not exactly controlling the same phase error which is given at an instant. It's changing continuously. Whereas for the negative phase error at a given reference edge, you are having that exact phase error at the input, proportional output, and you control the next reference edge. So if you see, for the positive and negative, the feedback is acting differently. Okay. So this is one of the non-linearity which is inherent to the PFD design. Like quite often this is, or I say most often this is not a problem, but this can be a problem sometimes. Pardon? Okay, so in the first case, when R is the reference and V is the feedback. So let me just show you on the PL. So this is your R signal, okay, and this is your V signal. So now what is PFD doing? It is, so if you see in this case, right, as soon as R goes high, up pulse goes high, right? When up pulse goes high, you keep on pumping in the current, means you inject current in this node, so your V control changes and hence your phi out changes and V becomes V dash, right? So the phase error at the reference which I was having initially, TE phase error, right? For that TE phase error, this V edge has actually moved in, if the feedback is right, right? So at the reference edge, there was some phase error, but what you corrected for the phase error was different in feedback loop. Look at the same case when you're having a negative phase error. In a negative phase error, as soon as your V goes high, your down signal goes high. This is down, right? And whatever your reference edge was, because you do not change the reference, you only change the V. So in a feedback loop, it is still controlling the V signal, but the edge which is going to change is the next reference edge, next edge of the V. Got that thing? So you see, for a same input means at the instant of the reference, whatever the delta phi error was at the input, it depends on the positive, whether it's positive or negative, that what are you correcting. Has the system been a linear, it should be just a linear gain in the system. Okay. So one part will be faster, other will be slower if you look at a settling point for given any phase error. Pardon? That's what I'm saying. It more like in many cases, most of the cases, it's not a problem, but it is inherent to the PFD. We are not doing anything to correct it. It can be a problem if the bandwidth goes too high and you want to change positive, negative quite fast. Okay. Any question? Okay. The next one. So the next one is your charge pump nonlinearity, which is again. So let me. So now let me just ask you this, that what all can go wrong here, and I think because this is more or less an implementation dependent. If somehow you can make it ideal charge pump, then it is fine, but there is nothing ideal as such. So this is I up, I down, up bar and down signal. Okay. So in this, what all can go wrong as such? So your I up is not equals to I down. Okay, I'm using uppercase and lowercase. So let me just, I up is not equals to I down, that is 1. So that will inject a delta charge every time. Okay, what else? Pardon? Channel length modulation. So the thing is, quite often you can fix the channel length modulation by, I mean, channel length modulation is surely there. So what I say is, you can quite often fix the static one. The static ones means, so this is one of the tricks which is being used. So let's say this is the loop filter, right? Another one, C1, C2. So this node is mostly a stable node. Okay. So let me just call this as VC dash. Now if I say, let's say VC dash is 0.5, you design your charge pump for I up equals to I down. But if your VC dash goes to 0.25, depending on the frequency requirement, right? Then the NMOS current source is ideally crushed. So what you can do is, you can take this VC dash and have a feedback loop to control I up and I down. So static variation you can easily control. That's some feedback loop. Okay. The problem comes with the transient. When the voltage changes, so as soon as you dump a charge, there will be change in the voltage on this node. So how does the transistor respond to a transient changes? Okay. So channel length modulation affects there. What is the another one? Let me just say. Yeah, so that is very right thing here. So at the end, if I up and I down on an average, so let me just, what you are saying, I am coming to that thing only. So let's say your, so let's say this is your I up signal. Okay. Now ideally, and I'm drawing only the reset phase, right? So ideally the down signal should also be exactly matched Ideally, the transient waveform should exactly match. If you do not want any delta I to be pumped into the loop filter at any instant of time. But what happens is, first thing is, because NMOS and PMOS, they have different gate capacitance, and even if you size the buffer accordingly, you may have a rise time difference on this, right? Rise time and fall time may differ, and so on an average you can still, so what can happen is, let me just show you, because of the difference in the up and time current pumped into the loop filter, you may have something, let's say this kind of thing every reference. It can happen. So this one is means you can say this part is coming because of the transient difference, and the other part is coming because of the static. On an average, if you look the one reference cycle, it is zero. So the voltage will V control will not change. The DC of the V control you can maintain zero in a locked state, but you will still have the transient current injection current pumped into the loop filter, and this will cause you the reference spurs. Okay, so it's a very like critical design of the very critical design for the charge pump, that you should have both static and dynamic. Static and the transient current up and down pulses should match, but nothing ideal. Okay, so so another one is not a non-linearity as such, but another effect which we have completely ignored so far is any delay in the loop. So you have a divider, the divider comes with a delay. Any digital block, if you are having in the system, there will be a certain delay associated with it. Means the VCO will also have some delay. I do not know, I can't say whether it's a 10 picosecond or 100 picosecond, but there is some delay associated with it. Same as with the reference, the same as with the divider. Okay, you are putting I am putting this, PFD flip flop. So the PFD flip flop itself has a delay. And these delays will control when the final edge is coming, right? The way I plot it is, as soon as the reference goes high and the V up goes high and the down signal goes high and ICP changes instantaneously, that doesn't happen. So all that delay can be modeled. So I think this part you might be familiar, that the delay can be modeled with a transfer function of e power minus std, right? Where td is the delay in the whole loop. Now, if e power minus std is the delay, and let's say the delay is much lesser than the reference frequency, how will the loop gain change? So I'm writing new loop gain is e power minus std times the loop gain which you are seeing up is the old loop gain. Okay. What will e power minus std? Now this is under approximation, that td is much lesser than the frequency which I am considering here. So just a minute. Sorry for this. Okay. So what will this do to the loop gain properties of the PLL? Your phase margin actually reduces, right? So the new phase margin is equals to old phase margin minus tan inverse of omega utd. Okay. Yeah. So you have to take this into account. If your means if the reference frequencies go high, then what is the total delay in the loop to get a desired phase margin? No, no, omega u will change. Means I'm saying if I still want the omega u. Uh, so the thing is, in the locking case, right? In the locking case, your divided output will always lock to a zero phase error with respect to the input. That means if there is only this delay is the case, right? The locking case should always be the zero phase error, because if there is, because if you, even if you have any static, let me just say, if you maintain any DC voltage here, right? Any DC voltage here, you have to keep correcting for the DC voltage, otherwise your frequency is just going to go high. Feedback ensure the error is there. No, so the thing, so okay, let me get your question. So what you are saying is, at the input of the phase error detector or the output of the phase error detector, the phase error is zero, right? But you are saying that the input of the divider may not be exactly n cycles away. Let me just put it that way, right? Because there is some delay associated with the divider. Yeah, that you are right for that. So the thing is, let me just say, whatever the delay of the divider is, right? You will change the voltage, you will change the phase accordingly, such that you compensate for the delay in the loop. Okay, but once it comes at the input, you lock it to zero. So your question is that, let me just repeat it for others, that the in a locked state, the phase error phi e is going to zero, but there is a delay associated with the divider. Okay, and that delay means, so it's like this. So let's say the input of the, it's a divide by 2 signal. So the output of the divider ideally is this. Okay, but because of the delay associated with the divider, let me just amplify that. So let's say the divided is this, right? Because of the delay through the divider. Now this edge is going to lock to the reference. So this one is reference and this is V. Your face can move. Please, the thing is, the law, you can say that the output edge and the divided reference edge, or sorry, or the, yeah, the output edge and the input reference positive edge, they are not aligned. Yeah. Okay. So yeah, so these are the sources of the nonlinearity in the charge pump PLL. I think by the end of this, everyone can design a basic charge pump loop gain analysis you can do, right? And get the desired phase margin and every bandwidth and other parameters. Okay. So now this another part which comes is the choice of bandwidth and the phase margin, which I told will start with the noise analysis of the PLL. So let's begin with that. Noise analysis of charge pump PLL. Okay. So before I go into the noise analysis, I would say there are only few basic noise sources, means the basic noise sources which exist in the PLL. So can you just point out basic noise sources in the PLL? See, there are some noise sources which are extrinsic noise sources. Let me, extrinsic noise sources which are not inherent to the PLL but which are coming from outside. And the coming from outside are supply noise, substrate noise. So you see all the noise sources which we have seen so far are like a voltage or current noise, right? The ripple on the supply or ripple on the substrate, and any coupling with an external thing. Coupling with external signals, external unwanted signals. Okay. They are the extrinsic noise sources, which depend means you can when you design the PLL, you see how much the extrinsic noise is coupling to the PLL, and then try to eliminate it or suppress it, whichever way you can do it. Yeah. Yeah, and so there are, so the thing is, depending on the kind of the substrate, right? You will this so are you asking the question what is the substrate noise, or you're asking the question how the substrate noise will get coupled to the circuit? Okay, so the substrate noise arises, so let's say you are having any digital block. Let me just give an example, right? So in a digital block you are pumping in a lot of current on the substrate when the substrate is a ground, right? Then so this is one thing, when you're pumping a lot of current on the substrate, there will be ground fluctuations, okay, and through the substrate that can get coupled to the other circuit. Okay, so just as an example, I have a digital block and I have this ground and same substrate, and let's say I have an oscillator, okay, and the oscillator also has a ground. Now if these two grounds are connected, which they will be on a same substrate in all regular cases, though we have ways to like separate them apart, but if you are having these two substrate connected, then you will have any current, any changes say here, any ripples here will basically get coupled to the other circuit. Okay, this is one thing. Then the other thing is, if there is any you can say random noise which exists in the substrate, okay, that will also get coupled to. But more or less, what is the basic substrate noise is what is getting coupled due to the other circuits. Okay, so that particular noise when get coupled to your actual ideal circuit, actual desired circuit, then that is a real problem. It's not coming from my VCO, it is coming from somewhere else, and I cannot even control that. Okay, same is with this. Now the supply noise can also come if your supplies are coupled. So in many cases you can keep the supplies different, right? But what about the substrate? So in a silicon, if you go into the chip design, when you have a silicon wafer, right, which is all P diffuse region. Okay, now this is all. So let me just. This is all P type, P diffuse silicon. On this you actually have a PMOS and NMOS, right? And all these substrate are connected. Means for PMOS and NMOS you will have a. So let me just say you will have NPN, and for NMOS, sorry, yeah, and for PMOS you will have PNP. Means you will change the other part. All, but they're all made on a same wafer, right? So there are ways where you can have a, like you can create a deep well around NMOS MOSFETs. Okay, they are called deep N well devices where you can separate them. So you can, so the thing in cases, if the circuits are very sensitive to any of the supply or the substrate noise, you create those devices, you make those circuits in a deep N well. Okay, and thus alienate all these circuits from the other part of the substrate. But some coupling will always be there, you cannot just eliminate. Okay. Same is with the supply noise. Okay, the other thing is coupling with external unwanted signals. You can say, let's say if the clock is let's say if your reference and your clock are running, let me just say here, let's say your up and down signals are running, right? Something, and they are running close to you, and this is actual line, wire. And if these are running close to your VCO frequency, okay. So if up and, so let me just give a better example. So let's say there is a supply of the charge pump, V supply of charge pump, and you have F out, which is VOP and VON. This is the PLL output, right? You have a capacitance connecting to both of them. You are coupling from the supply. Any ripple will then capacitively get coupled. So then you try to have a, like you try to have a ground shield around it. Keep them spaced apart such that the coupling doesn't change the desired signal. Okay. So these are all the extrinsic noise sources. Then this, what is intrinsic to the PLL? Means the noise which is generated within the PLL. So can you just point out intrinsic noise sources? I am asking very basic element. VCO charge pump is one level higher, some little bit lower. Yeah, charge pump current source noise. So that is like a basic transistor, right? If I NMOS or PMOS. So transistor has a noise, thermal noise and the flicker noise, which is modeled. I hope everyone knows this. So IN, the noise spectral density of, so S of, okay, let me just say, the noise spectral density of the any current source is equals to 4 kT gamma times GM, or 8 kT by 3 GM, right? If it is operating in the as a current source. And the other noise source is a basic resistor. You can model this as a current source or a voltage source, that depends. So if this is R, then S of current source noise is 4 kT by R, where K is a Boltzmann constant. You write K as a small or capital? I am just thinking about capital, right? Okay, I'll check it. Huh? Capital. Yeah, I was thinking it's a small or something. Okay. So these two are the basic noise sources which will cause all the noise in the system. Okay. So how do we analyze the noise for the PLL? Is that we know that this is the basic element which will cause the noise, but we like categorize all these noise, not categorize, we just find the noise sources of each circuit block and then use that noise source to find the total output noise. Okay, so the procedure would be, so let me just say, we figure out all the noise sources in the system. So let me just say you have, so input Phin is coming, so that will, there will be some noise which is added with the reference. Okay, so now this is modeling all the noise sources. So S of, so let me write S of Phi in. So this is coming slightly bigger. So S is the noise spectral density, S of Phi in. So S of Phi in is power spectral density of reference noise. Okay. and this should be in proper dimension. Like it should be something unit for this will be radian per square hertz. I'm finding the noise in terms of phase here. Okay. The radian square. So I'm looking at a noise spectral density, right? So power spectral density. Sorry. So this should be radian square per hertz. Okay. Now the next one is the charge pump and PFD. Okay. So PFD can also cause some noise depending on the switches which you are using, and the other one is the charge pump. In most of the cases, the charge pump noise dominates. So I model the charge pump noise as S of ICP. Okay. So the thing is, I need to find where all these noise is added in the loop, and then find what is the contribution of these noise sources to the output. Okay. So I'm just trying right now. I'm just finding all the noise sources in the system. This one is the charge pump noise. Then you have a resistance noise. Okay. So let me. This is something which is quite often. Okay, C1, C2, and R. So for this, ideally the noise sources attached to this here, right, is not actually attached at the output of the loop filter. There will be a difference. You may see a minor difference between the two, but the exact point is this. Okay, so if I want to see it in terms of voltage, then the voltage would be something here. Let me just VNR C1. Okay, and then you have the VCO, which is KVC over as the transfer function, and then the noise is added at the VCO, which is S VCO. Again, this is the phase noise, S phi VCO, and in the end you have a divider. Some noise will come with the divider also, S phi divider. Okay. So the noise sources which we have identified so far are charge pump reference noise, charge pump noise, power spectral density of charge pump noise, then you have the resistance S of R, resistor noise, S phi of VCO. This is the noise contribution due to the VCO, which is added at the output due to the voltage control oscillator. It can be current control also, and then you have a divider noise. Divider. So all these noise sources exist in the system, and now I need to find the noise due to these noise sources to the output. Okay, so let me just begin with the first one, noise contribution to phi n out. Phi n out is the total noise at the output. Okay, so for doing this, what shall we find out? I know that this charge pump can be modeled with the, or any of the circuit block can be modeled as a total output or input referred noise. Okay, now I need to find the noise contribution to the output. What should be the next step? Pardon? Find out the transfer function from from wherever the point it is, the noise is being injected to the output. So those things are called as noise transfer function or NTF and so let's now start with the NTF of the input. What is this one? This will be quick. So I just need to know the in terms of loop gain, right? What it should be? What is it? Yeah, n times loop gain by 1 plus loop gain. Okay. Now what about the for the charge from noise? N into ICP by okay, you can write it in that manner or you can refer it to the input. Okay, and then that will become the same as NTF of input. So that transfer function is 2 pi by ICP. I'm just ICP by 2 pi is the gain factor. I am just dividing it before. So this will be 2 pi times ICP into NTF of input. Okay. Then what about the yeah. Huh? Okay, so let me just do it the basic way. So what you have is for the ICP wherever we are adding, right? We have loop filter of S times KVCO over S, right? Divide by 1 plus loop gain. Okay, so this will be now I'm just multiplying to ICP by 2 pi into loop filter of S. So let's say if I multiply ICP by 2 pi on both the sides, GS by 1 plus GS HS, yeah, okay. So 2 pi, this one is, I am multiplying and dividing. So ICP by 2 pi and 2 pi by ICP. Okay. Now this particular itself is what? N times loop gain, right? Now the loop gain takes the 1 by n factor into account. Okay. So what about the resistance one? This is little bit tricky. So let me just, where did I plot it? So let's say you find this V and R to V control some transfer function. Just the loop filter means what I am trying to say is you have C1, C2, V of R and V control. Okay. So you find V control by VR, then I will leave that part. So V control S by V of R transfer function. Okay. And this multiplied by, now this will be only KVCO over S divided by 1 plus loop gain. So I found will V control. V control to output is only KVCO over S. Okay. Then you have NTF of VCO which is 1 by 1 plus loop gain. Okay. And the final one is NTF of divider which is also equals to, so n times, which is same as your input. Now we find all the noise transfer function. What will be the total noise? Phi n of out. So the thing is, first we find the total noise spectral density. Okay, which will be now S total output will be equals to S of phi input multiplied by NTF of input square, right? As well, in terms of power, NTF is just a transfer function, so it will be squared. Now S of ICP times NTF of charge pump square. I write ICP, okay. We can change it to CP in some, let me just say that is better. So, okay. So you can find all these noise sources. So let me just write it here and then finish off. So S of R into NTF of R whole square plus S of VCO into NTF VCO whole square plus S of phi divider into NTF of divider whole square. So you can find the total noise spectral density in this manner. Given you find the independent power spectral density for all the noise sources. And we can calculate jitter from here. Let me stop here and we'll continue tomorrow.